Because LLMs are trained on a large corpus of data, you may need to customize an LLM for a special use case in order to improve its accuracy, effectiveness, and adaptability. Methods that improve LLM performance include prompt engineering and supervised fine-tuning, which are considered traditional approaches. Retrieval augmented generation, or RAG, and parameter efficient tuning, or PEFT, are considered more advanced approaches. Let's begin with an overview of prompt engineering and supervised fine-tuning. Prompt engineering focuses on crafting effective prompts or instructions that guide the behavior of the LLM to perform a special task without the need for task-specific labeled data. Instead of fine-tuning the model's parameters on task-specific data, prompt engineering relies on designing prompt templates or patterns that bias the model towards producing desired outputs. Prompt engineering requires no training and sometimes no coding. Here is an example of a few-shot prompt. This prompt provides key elements for developing a comprehensive marketing strategy tailored to the target audience and product attributes, guiding the business towards effective promotion and sales growth. The few-shot examples include product features, channels, and messaging. This is a basic example prompt engineering code using Hugging Face's Transformers library in Python. In this example, the code generates text based on a given prompt using a pre-trained language model. Here's what each parameter does. Input text. The prompt or input text to generate text from. The model generate method generates text based on the provided prompt. It takes several parameters. Tokenizer.encode, input text return tensors equals PT. Encodes the input text using the tokenizer and returns it as PyTorch tensors. The tokenizer converts the input text into token IDs that the model can understand. Max length. The maximum length of the generated text. The generation process stops when the text reaches this length. Temperature. Sampling temperature controls the randomness of the generation process. Higher temperatures result in more diverse but potentially less coherent text, while lower temperatures lead to more predictable but potentially repetitive text. Top K. Top K sampling limits the vocabulary to the top K most likely tokens at each step of the generation process. It helps control the diversity of the generated text. Top P. Top P sampling, also known as nucleus sampling, limits the vocabulary to the smallest set of tokens whose cumulative probability exceeds the given threshold P. It dynamically adjusts the vocabulary size based on the probabilities of tokens. Num return sequences. The number of sequences to generate. And this parameter allows generating multiple sequences based on the same prompt. Pad token ID. The token ID used to pad sequences. In this case, it's set to the end of sequence token ID obtained from the tokenizer, tokenizer.eos_token_ID. So finally, we decode and print the generated text. This code takes the generated token IDs, converts them back into text, and prints the generated text, making it easier to read and interpret the model's output. Generated text accesses the first generated sequence from the list of generated sequences. Each generated sequence is represented as a list of token IDs. Tokenizer decode decodes the list of token IDs into human-readable text using the tokenizer. It reconstructs the text from the token IDs while skipping any special tokens, for example, padding tokens or end-of-sequence tokens. And skip special tokens equals true. Indicates that special tokens should be skipped during decoding. This ensures that the generated text doesn't include any padding tokens or other special tokens added during tokenization. Prompt engineering involves experimenting with different prompts, instructions, or templates to guide the model's behavior towards desired tasks. You can customize the prompt according to the task you want the model to perform and adjust the generation parameters based on your requirements.